We're now going to look at more complicated optical systems. So we looked at simple single lens systems, a diverging or converging lens or a diverging or converging mirror. But back in the 1600s and even earlier for telescopes, physicists realized that if you use lenses in combination, you could actually achieve some fairly amazing things. So lenses can be combined into multi-lens systems. So those lenses reinforce one another or can provide additional abilities such as significant magnification. So the first we're going to look at is microscopes, and then we'll move on to talk about telescopes. Two, in their very simple sense, basically two-lens systems. A microscope is a simple two-lens system, as is a refracting telescope. Modern telescopes are far more complicated. Modern microscopes are far more complicated. But you can create a very simple compound microscope, they're called, using simply two lenses. So a compound microscope uses two lenses. One is called an objective lens, and that's the lens closest to the object. And the other is the eyepiece, which is not surprisingly the lens closest to your eye. By combining these two lenses together in the diagram shown here in just a moment, you can see that the light rays bend as they go through both lenses, allowing an image to be magnified significantly and to then, of course, the light rays come off the eyepiece parallel, those light rays go into your eye, focus in on the back of your eye. So technically it's kind of a three-lens system. You have the objective lens near the object, you have the eyepiece, and then, of course, your actual eye lens to focus the object on the back of your retina. So the magnification for a compound microscope depends on the magnification of the individual lenses. So you would have to go through and calculate for the objective lens. How far away is the object? What's the focal length of the objective lens? What is the image distance formed by that lens? And then calculate the magnification for lens number one, the objective. Then, knowing where the image is for lens number one, the image of lens number one becomes the object of lens number two. So you measure the object distance between the first image and the eyepiece, calculate what, you'll given the focal length of the eyepiece, calculate what the image distance is, and then you can calculate what the magnification is of the eyepiece. And the total magnification of the microscope is the product of those two magnifications. So if the objective gives you a factor of 10 magnification and the eyepiece gives you a factor of 15 magnification, the total would be 150 time magnification for that microscope. Now, this has a practical limit. You cannot, sadly, just keep on putting in more and more powerful lenses and see down to the individual atoms. There are a lot of limitations for microscopes, the main of which is actually the wavelength of light we're looking at and the aperture we're looking at. So normal microscopes can magnify up to 1,500 times, 1,500 time magnification. So it can see bacteria. You can see hair follicles and cells. You might have done this in a biology course at some point in the past, used some kind of a stain to bring out red blood cells or white blood cells. But you can't really see much beyond that using a normal compound microscope. Scanning electron microscopes, we will learn later on, can actually see very, very small objects. But we're limited for normal microscopes to about 0.2 microns. So that a micron is a millionth of a meter, so this is 2 10-millionths of a meter. So this gives the limitation. So we can see very small things. I mean, in ancient times, we didn't know what carries disease, but we now know bacteria. Little tiny one-celled organisms exist, and you can see them using compound microscopes. But viruses, you can't see using a compound microscope. A virus would be too small. Now, three parameters that describe microscopes, which we'll explain in more detail in the next board. We're going to talk about the numerical aperture, or NA, of a microscope. We're going to talk about the magnification of a microscope, a bit what we talked about here. And we're going to be talking about what's called the working distance. So these three things together sort of define the abilities of a given microscope. Looking at these three terms that define a compound microscope. The first, again, is numerical aperture, or NA. It's related to the light gathering power of the microscope. For the microscope to work, you have to be able to look through it and see the specimen, the light reflecting off the specimen. So a lot of microscopes might have you place your specimen on a clear glass plate with some kind of a dye or some kind of a fluid to suspend it, and then place a slide cover on it to press between that and the glass plate. That'll be your specimen. That goes under the microscope. And of course, then you might have a light underneath the microscope to shine light through the specimen so you can get it into your eye. If no light goes through the microscope, you cannot see the specimen you're looking at. So the numerical aperture is a measure of how well you can see and therefore how much detail you can get from the specimen you're looking at. Now it depends upon what's called the angle of acceptance, and here it's theta. The angle of acceptance is just basically the angle formed by the cone between the specimen that you're looking at and the lens. So hopefully you can see that the closer the lens is to the specimen, the larger that cone will be. So light's coming off this specimen in all directions. It's, light is striking it and it's going off in all directions. The further away the lens is, the smaller this cone and the smaller the amount of light that goes through that lens. So the numerical aperture is given by the equation n times sine alpha. Now alpha is the half angle here. So if you know what theta is, just divide that by 2 to get alpha. N is the refractive index. We talked about N when we talked about the refractive index of lenses, the materials you can make lenses out of. Now, the refractive index of the medium between the lens and the specimen. Now, for most of this stuff, it's going to be air. But you can actually use alcohol, oils, transparent oil, water to increase the refractive index. If you increase the refractive index, you increase the numerical aperture. The way to think about that is, remember, the refractive index measures how well light can bend, or how effective a material is at bending light that enters it. So if you have a material that is more effective at bending light, you can capture more of that light. So the bigger the numerical aperture, the more detail you'll see in a specimen. We talked about magnification already in the last part of this video, but magnification is just the product of the magnification of the two eyepieces, the two lenses, one eyepiece, one objective. And then finally, the working distance. The working distance is just how far away is the object from the lens. So that distance, the closer you are, the more light you'll capture and the larger the numerical aperture. But you have to be careful, of course, and I've done this, I remember in biology class, you might have too, where you zoom in, reduce the working distance as you move the telescope objective lens down closer to the object, and you actually get so close you crack the plate, right? You break the glass slide, right? You can't have a working distance of 0. There has to be some space between the object you're looking at, the specimen, and the lens. So in terms of microscopes and photography, F number is a popular way of looking at it, especially in photography. If any of you are amateur photographers, you've probably heard of the F number of a lens. It's a measure of what's called the speed of the lens, or how fast the lens is. Of course, lenses themselves are just bits of glass or plastic. They have no speed, but rather it's how fast you can expose a photograph. So the faster a lens, the shorter the exposure time in capturing an image. So for instance, in sports photography, or when filming children that are running around, you want a fast lens, so you don't have to have a very long exposure time and your exposures aren't blurred. If you're doing wedding photography, while people are standing there smiling and not moving, you don't need a particularly fast lens in order to capture a brightly lit room with non-moving subjects. So the F number is just basically the light per unit area that hits the image plane. The smaller the F number, the faster the lens, and the more light you get into your system. So it's kind of the opposite, or the inverse, of the numerical aperture. A big numerical aperture number is good. It refers to getting a lot of light in. A small F number is good. And you can see how they're inversely related here. So the F number is really the focal length of the lens over the lens diameter. So if you have an actual lens, if you measure its focal length and you measure the diameter of the lens, divide one by the other, and that tells you the speed of the lens. So you want a small F number, so a short focal length or a big diameter lens will give you a fast lens. If you've ever watched sports, especially football, on the sidelines, you see cameramen and camerawomen, right, with these huge, long lenses with very, very large pieces of glass in the front. A big diameter lens gives you a fast or low F number lens. It's approximately equal to 1/2 or 1 divided by 2 times the numerical aperture. Not half the numerical aperture, half the inverse of the numerical aperture. So 1/2 times the numerical aperture. So a big numerical aperture, big NA, gives you a small F number because, again, they're inversely related. So this gives us a sort of an understanding, a basic understanding of the simple compound microscope. Microscopes today can be very, very complicated, and we'll talk a bit about the resolution limits of microscopes. We talk about wave theory of light, and we'll also talk about scanning electron microscopes when we talk about the atom and quantum mechanics, which is later on this semester.